Wait, already? Can you put the presentation so that we see the title? It's easier to got it. So yeah. Okay, welcome back. So we continue our afternoon session with talk from Giulia Gubitosi from University of Naples. And she will speak about interplay between spacetime curvature, speed of light, and quantum deformations of relativistic symmetries.
Thank you, Maria, for the introduction. Thanks to the organizers for inviting me to give a talk here. Some of you asked me about a previous title I had, so apologies if you came here to hear about the coherence. You'll hear about that next year, hopefully. I decided to talk about this other topic in the end. So in this talk, what I'm going to discuss is, so we know that we have heard here about quantum deformations quite a lot. We are going to hear more in the next days. And what I want to discuss here is how quantum deformations interact with other kinds of deformations of symmetries that we may have, which are classical deformations. For example, deformations induced by curvature of spacetime, or the deformations that that involve the speed of light. So in particular, contractions to Galilean limit or to Carolian limit. Let me start from the very, okay, before we start, so what I'm going to tell you is result of all of these works in collaboration with the group in Burgos of Ángel Ballesteros, Francisco Herranz, and Ivan Gutierrez Sagredo. So if when there are no references in the slides, is because what I'm saying can be found in these papers here. So let's start from the very basics. And so what I am interested in particular are relativistic symmetries and the ones of special relativity. And they are described, as we all know, by the Poincaré algebra that is generated by time translations, space translations, boosts, and rotations. And this is the algebra, you all know it. And this is the first Casimir of the algebra. This is the algebra of flat Minkowski spacetime, which is the homogeneous space that can be obtained via this quotient. So what we're going to discuss today is all possible ways to deform these kind of algebras and ways that are of interest for physics, for phenomenology. So when in some cases I will make brief excursions to say why the deformations I'm considering are relevant for physics. Okay, the first kind of deformation we're going to talk about is a classical deformation. Also, this one you probably all know about it. It's a deformation that is governed by a curvature parameter, lambda. Of course, when we want to deform an algebra, when we want to deform the Poincaré algebra, we need a deformation parameter that has dimensions. Otherwise, we do not have, we cannot create new structures. In this case, this parameter here has the dimension of a squared length. And so this kind of deformation is relevant when we are at very large length scales. And for example, when we want to consider a cosmological setting, so de Sitter or anti-de Sitter spacetime. Here we have de Sitter or anti-de Sitter because we are doing deformations of the Poincaré algebra, so we are always going to have maximally symmetric models. So we have 10 generators of symmetries here, and we always want to keep the 10 generators. So for this reason, I'm not talking, for example, about Friedman, Robertson, Walker models. But okay, this is so when these kind of symmetries here would be relevant for a de Sitter universe, let's say, or anti-de Sitter. So how does this deformation work? It brings us from the Lie algebra of Poincaré to another Lie algebra. So you see that the deformation appears here. And this is what curvature does in general. It induces non-commutativity between the generators of translation. So this is what happens here. This is still a Lie algebra. You see that all the commutators are linear. And the curvature parameter also deforms the Casimir of the algebra in this way. The corresponding spacetime of this algebra, as I said, is the de Sitter or anti-de Sitter spacetime, depending on the sign of the cosmological constant. And because this is a deformation of the Poincare algebra, we recover the Poincare algebra and Minkowski spacetime in the limit where lambda is going to 0. Yeah, this is what I just said about the role of curvature. So here it's the first brief mention of physics. So let's say that I am in this de Sitter universe, and I want to see how a particle is moving in the de Sitter universe. So this would be the metric of the de Sitter spacetime. I'm going to work in 1 + 1 dimensions. This is the same algebra that I have here, with the difference that this is in a kinematical basis. Here I am in the co-moving basis, which is the one that is most appropriate to work with these cosmological coordinates. But it is just, yes. Not the group, the algebra. So I'm just, yes. You see, it's just adding this term here in the commutators. You can add it. What you can check is that you have a smooth limit back. And I mean, this algebra was not built originally as a deformation of Poincare. It was born to describe the de Sitter symmetries, and then you can check that you can go back.
If I can say something, it's the opposite of Inoue-Wigner contraction.
Ah, yeah, exactly. Yes, if this is, yes, so it's easier to talk about the contraction rather than the deformation, but yeah, you recover that.
SO31 has no action on algebra, no?
Sorry?
SO31 has no action on this group, on the algebra. Because the tensor you're writing for the T, it's not the invariant.
Sorry.
You're writing
Here.
That doesn't seem invariant under the action of the Lorentz group.
Lorentz group is a subgroup of this algebra. So you see, well, here we are talking about algebras, not groups. But you see that here the boost sector is the Lorentz sector is well, does not close because there is the commutators between boost and P. But you have a
I'm talking about last column.
Here.
Why is it invariant under the action of the Lorentz group? On P8. SO31.
Yeah.
How does it act on the P?
It acts, I mean, the P is transformed.
On the tensor or the at least to me, it doesn't seem invariant. Epsilon ABC is not invariant under SO31.
Okay, so this algebra, so we can go back. The de Sitter spacetime of which this algebra describes the symmetry, you can see it as an embedding of a larger Minkowski spacetime, higher dimensional, 4 + 1 dimensional Minkowski spacetime. So you can look at the SO41, so it's the Lorentz symmetries of the Minkowski, higher dimensional Minkowski space. Then you embed, you do an embedding, and here, and you obtain the de Sitter. And this algebra here, you can obtain it by projecting the Minkowski, higher dimensional Minkowski algebra to this lower dimensional manifold. Does that help? Okay.
It's
So
just
but lambda not equal to 0, it's SO31. What does that mean? There is no action.
this is the algebra of SO14 or
Yeah.
SO23, depending on your signature, and
Yeah,
it's just
this
written
one.
non-covariantly. So it's a,
Yeah,
it's
I
a
mean,
Lorentz algebra.
Yeah, probably it's the way it is written that is not apparent. But I mean, for lambda negative, this is SO32. For lambda positive, this is just SO41, and that admits this quotient. Okay. Well, maybe I can continue. Yes. Okay, so I was saying I want to see what a particle moving on this de Sitter spacetime does. And to do that, I just define a phase space for the particle given by coordinates and momenta in the standard way, that is this one. I can find the representation of the generators on the phase space of the particle. And from here, for example, looking at the Casimir of the algebra, I can work out the on-shell condition for the particle, which encodes the well-known energy redshift that we know that a particle has because of curvature. And in fact, it depends on h, which is square root of lambda. And I can study the world length of this particle using just the Casimir as the Hamiltonian of the free particle and work out what is the world length for the particle. So this is, everything is very, very well known. It's just to set a formalism that I will also use later. Okay, so now we have talked about classical deformations. Next step is to look at quantum deformations of the Poincare algebra. I'm going to talk about a specific quantum deformation, which is the kappa quantum deformations. Of course, there are other possible ways to define quantum Poincare algebra. I will talk about this one specifically. So we can think about it as another direction in which we can deform the algebra. What happens here is that this kind of deformation does not produce a Lie algebra again. It produces a Hopf algebra, which has some additional structure. So from what we had before, for example, what happens is that the commutators get deformed, but in a non-linear way. So in particular, in this specific basis, which is the bicross product basis, what is deformed is the commutator between boost and translation in this way. And also the quadratic Casimir becomes, well, what was the quadratic Casimir becomes this object here. Besides the commutator between the generators, we need to define some additional structures, which are the so-called coproducts, which give us basically the action of the generators on multi-particle states. So in the usual case, when we have a Lie algebra, the action of the generator is just according to the Leibniz rule. When we have a Hopf algebra, this is deformed, and this is what we get in particular for the kappa Poincare Hopf algebra. So we see that these first two are still trivial, but then space translations and boosts are deformed with deformation governed by the quantum parameter kappa. Here, just a note. So just a note, this is not how the kappa Poincare algebra was derived originally, but this will be useful later. One way to construct the kappa Poincare algebra as a Poisson of algebra, so it's a kind of a semi-classical version of the full of algebra, is by using this R matrix here. From here, you can work out the co-commutators just using the commutator between the R matrix and the generators of the Poincare algebra. And from here, you work out what are the coproducts by looking at by exponentiating the dual algebra to these generators. I'm not going to go into the detail. It is just to let you know that this is one way to construct the kappa Poincare Poisson of algebra. And then when you quantize it, you recover the full kappa Poincare of algebra. Let's go back to what happens to a particle that behaves according to this other deformation of relativistic symmetries. Earlier, we have seen what happens to a particle that behaves according to the classical deformation. Here is according to this quantum deformation. Again, I define a phase space for the particle in the standard way. I represent the generators of the kappa Poincare. Again, I'm in 1+1 here. I represent the generators of the kappa Poincare algebra on this phase space, and I can work out again with the same Hamiltonian formalism that I used before, what is the world line of a free particle. And in this case, we get an interesting result, which is that the velocity of a particle is deformed in this way, and in particular that for a massless particle, its velocity depends on P0, which is the energy. So this is what generated all the interest from people doing quantum gravity on these models, because there is some potential for phenomenology here. Just a few more slides on this. So this is the kind of phenomenology you would expect. You have two particles that are massless. You emit them at some observer Alice. They have different energies, so they reach observer Bob at different times. And the way to look at this is to write down the word lines as seen by Alice and then compare them by acting on the word lines with the translation generators to see what the new observer Bob sees. For those, you probably know that these coordinates here, which are Poisson commuting, are not the ones that are usually considered in the context of kappa deformations. The coordinates that are usually considered are non-commutative coordinates, which in this Poisson, which in terms of Poisson brackets satisfy these relations. So these are like the Kappa-Minkowski coordinates that are non-commutative. Here they are non-Poisson commutative. So I can also define a phase space according to these coordinates here that are related by, that are obtained by a definition of the coordinates I used before. What is interesting about these coordinates is that if I use them, then I get that the speed of the particle does not depend on its energy any longer in terms of these coordinates. However, the way translations act on these coordinates is non-trivial. So in the end, the two effects compensate. So what I would get is that, again, from the point of view of observer Alice, particles are emitted at the same time. Then I translate to see what observer Bob is seeing. And Bob is seeing that the two particles arrive with some time shift that depends on the energy of the two particles. And the amount of time shift is the same regardless of which of these two sets of coordinates I'm going to use. So until now, we have talked about curvature deformation and quantum deformation. What is interesting is that at least in the 1+1 dimensional case, sort of duality between these two deformations. So here is the phase space of a particle living on the Sitter spacetime, which is what we have considered at the beginning. So here you see this is the phase space. This is the Poisson brackets between boost and the coordinates, between boost and momenta, and this is the Sitter algebra as we wrote it earlier. On the other hand, on the other side here, we have the phase space of kappa Poincaré that we just used. And you see that the structures are very similar if I exchange P and X on the two sides. In particular, what we see is that if I take the De Sitter algebra, the Casimir of this algebra is determining the dispersion relation. And this algebra here has exactly the same form as the algebra generated by Boost and the Kappa-Minkowski space-time coordinates in this other side. And the Casimir of this algebra, in fact, is what defines the word line of a particle. On the other hand, if I look at the algebra generated by Boost and coordinates on this side, this algebra here is very similar to the algebra generated by N and P on the other side. You see it here. They have exactly the same form if you exchange X with P. And on this side, you generate the word line using the Casimir of this algebra, and here you generate the dispersion relation. So why is there this kind of duality here? It is because in the end, on one side, we have curvature on space-time, and it turns out that on the other side, one way to describe what is happening is that you have curvature on the momentum space. So there is really this kind of duality of having curvature on either side of the phase space. I'm not going to say much about this because I'm quite sure that Jurek will say more on Thursday about the momentum space of kappa deformed models, but this is what is happening here. And this is related to an observation that Majid made several years ago, that of algebras, when you have non-commutativity on one side, you usually have curvature on the dual space and vice versa. So this is one way to look at at this feature from a more physical point of view. Well, this I don't need to discuss it. Okay, so until now we have done either classical deformation or quantum deformations. In fact, what you can do is to consider both at the same time. So you can consider a quantum deformation of a de Sitter algebra. Let me just check. Okay. You can consider quantum deformation of a de Sitter algebra, which is called kappa de Sitter or kappa anti de Sitter, depending on the sign of lambda. So as I said, curvature is relevant for large distances. Kappa is an energy scale, so it's relevant in cases where you have energies comparable to kappa. And if you say that kappa is of the order of the Planck energy, then it's very high energies. This classical plus quantum deformation would be relevant for very high energies and very large distances. And in particular, it is interesting if you want to study, for example, if you want to study the propagation of very high energy particles, like we were saying before, but over astrophysical distances, so coming from astrophysical sources. And this is very relevant because it's what it's actually being done in phenomenology of quantum gravity. So I mentioned how you can derive the kappa Poincare algebra from an R matrix earlier, and I did it because this model here at the moment only exists in the Poissonov version. So it is derived using an R matrix, which is this one here. Notice that the parameter eta is just minus the square of the cosmological constant. So when you see eta, think about curvature deformation. And this R matrix is just the one that generates kappa Poincare, which is these first three terms, and an additional term here governed by eta. Notice that this R matrix here is the only possible expansion of the R matrix that is generating kappa Poincare if you ask that the time translation generator has a trivial coproduct in the end, which is reasonable if you think about this as an energy. So from here, as I mentioned before, you can produce the co-commutators computed in this way. I'm not going to discuss them. I'm going to discuss directly what happens to the structures that you build from here, which is the Poisson bracket and the coproduct. So again, this is what we had to begin with, and now we want to deform with lambda and with kappa at the same time. The first notable thing that happens is that the algebra of the translation generators gets deformed. You may remember that it was deformed because of curvature in the de Sitter algebra, but it was not deformed in the kappa Poincare algebra. And in fact, what happens is that here all the terms all the deformation terms are governed by eta, so they go to 0 when you have no curvature. So you recover what you have in the kappa Poincare case. The effect of having the quantum deformation is that this algebra is nonlinear. So at the level of the generators of translations, you can kind of separate the effects of the quantum and the curvature deformation, because one is generating the nonlinearity and the other one is making the commutators, the brackets non-zero. Even more interesting is what happens to the rotation sector. The rotation sector was completely untouched in both the curvature deformation and in the quantum deformation. What happens here is that not only it is deformed, but it is deformed in such a way that it is breaking isotropy, because you see that there is a special role for one of the rotation generators. And this effect here is a purely quantum plus curvature deformation effect. So it would not be there if one of the two deformations was not there. So it is really something genuinely due to the interplay between the two kind of deformations that we are doing. And you see this both at the level of the algebra and at the level of the coproducts that are written here. You can also see, so we were talking about what happens to particles, and you can also see the effects of this double deformation at the level of world length of a particle. Yes.
So this is something I couldn't understand it. So in order to have a deformation, you really need to introduce deformation in the relativistic spectrum. You need to introduce the direction somehow. There is no
Yes.
way. So what is actually?
Well, you can pick one.
No.
There is.
That in the case of kappa Poincaré, you have the. I'm sorry. You have this deformation of the space versus time because explicitly kappa is actually a time-like vector, right?
Yes.
And here I don't see any point in which you actually break or deform the rotational invariance because there is nothing, no three vector that you introduce here. So
practice,
how this
yes, it is hidden. I mean, in the same way, when you do the kappa Poincaré deformation, you have a vector. I mean, you could do more general deformations. You could have light-like deformation. No, so you are fixing a vector there. You're fixing a 4-vector to a specific direction, which is that direction. Here, in fact, you do have the same thing. In principle, you have a vector. You fix it in the moment you choose the generators that you're putting here. Okay, so it's exactly the same thing. It's just that in the kappa Poincaré case, it looks more natural because you're just you're making time preferred direction. So it looks a bit more natural. Here, you're making a preferred direction in space, which looks less natural, but it is exactly the same kind of thing. Yeah, so here I chose to use the direction 3 as preferred direction, but yeah, you can think about having a vector here. What I was going to say is that we can look at what happens to particles when you have this this double deformation. However, this has only been done at the moment for the 1+1 dimensional case. So the kind of procedure that I showed you before for the kappa Poincaré particle and for the Sitter particle. The difficulty is that in 3+1 dimensions, it's non-trivial to find a representation of all the generators on the phase space of the particle, as we have done in the other cases. So at the moment, we only have the 1+1 dimensional case. But already here, well, you don't see this deformation of isotropy because we are in 1+1 dimension, you cannot see it, but still you see the interplay between curvature and quantum deformation parameter. Because, for example, so this is the formula that is encoding energy redshift. This is the part that comes from curvature, purely from curvature, the same that we had before. But here you see that we have a deformation of the energy redshift formula that depends on the product between L and H, so between the two deformation parameters. And the same thing happens for the word line of the particle. This was the deformation that we had before. Here I am expanding at the first order in L, but it's exactly the same thing. And then we have a correction to the energy dependence of the velocity of the particle that depends on the product between H and L. And this has observable consequences. For example, if you look at the time shift, the same that we had in the kappa Poincaré case, here you have the same time shift you had before, plus a term that depends on the product between the two deformation parameters. So you already see some things. You don't see this here. You cannot see this non-isotropy, of course. Okay, so until now we have talked about two ways to deform the Poincaré algebra. The last third item I want to introduce. So here we have two parameters, curvature and quantum deformation. In fact, in the algebra here, there was one parameter that was hidden because I set it to 1, which is the speed of light. But it's another parameter that is characterizing the algebra. And what happens is that I can contract the Poincare algebra in two ways. One way is the Galilean contraction. So this would describe the symmetries, for example, of Newtonian physics. It is a contraction such that 1 over c is going to 0, so speed of light going to infinity. And in the Galilean limit, we know that the light cones are opening. There is another contraction that is a bit less known, that is the Carroll contraction, where c is going to 0 instead. And in this contraction, the light cones are closing along along t. So in one case, in the Galilean case, we have absolute time. With this, we all know it. In the Carrollian case, we have absolute space. When you have curvature, so you start from de Sitter or anti-de Sitter, you can do the same contraction and go to Newton-Hooke spaces or curved Carroll spaces. This was all described in these very nice papers by Lévy-Leblond and collaborators. So in the Galilean case, what you do, well, you first need to reintroduce the speed of light by redefining translation and boosts. In this, I'm only writing the commutators that get affected by this. So these are the commutators. And you perform the limit and you get the Galilean algebra. So what is the Galilean algebra telling you? First of all, the commutator between boost and translation is 0, which means that you have an absolute time. This is the algebraic way to say that you have an absolute time. Then you have that boosts commute, which is telling you that you are in a non-relativistic regime. In particular, you do not have any longer the Wigner rotation, which is the typical feature of Lorentz symmetries. And finally, what happens is that even if I started with curvature, in this limit, curvature disappears. So I told you that a sign of curvature is that translations do not commute. Here, even in the curved Galilean models, translations are commuting. So this is already a non-trivial way that this 1 over c contraction interacts with the curvature deformation. In the Carroll case, again, you need to introduce the c parameter. You do it here in this way. And when you perform the limit, we see that, again, we get commuting boosts, which again tell us that there is it's some kind of non-relativistic regime. Usually this Carrollian limit is called ultra-relativistic because you are sending the speed of light to 0. So every other speed is infinite from this point of view. The fact that boost and time translation commute tells you that you have absolute space. And here, differently from what we did in what we saw in the Galilean case, you have that translation generators are still non-commuting when there is lambda. And here is just a table to recap what we found until now with these contractions. So in the center is what is the properties of the de Sitter or anti-de Sitter algebra. In the Galilean limit, we have absolute time, commuting boosts. In the Carrollian limit, we have commuting boosts and absolute space. And the only difference between the two contractions is that in the Galilean case, space translations commute, which means that the spatial slices that we can do in the Galilean case, so the metric of Minkowski when we go to Galilean limit becomes degenerate, and what you have that for every fixed time you have a spatial slice, and this the fact that this commutator is 0 is telling us that these slices are flat. Finally, let's go to the full picture, and let's add the quantum deformation to this story. So at this point, we have each corner of these squares is a different relativistic model, where you can have either curvature or quantum deformation or a speed of light contractions. And these are all possible relativistic models that one can study and see what their phenomenology is. So how to consider the speed of light contraction when we have a quantum deformation? One way to do it is to work again at the level of the R matrix. So perform the same kind of contraction that we have seen in the classical case a few slides ago. So the same kind of redefinition of the generators, for example, and the same limit. This is the Galilean case at the level of the R matrix. In fact, what happens is that when you are dealing with the quantum algebras, you can either do the contraction at the level of the R matrix or do it at the level of the co-commutators. The two procedures are not necessarily equivalent. And in fact, for the Galilei contraction, they are not. If you try to do it at the level of the R matrix, you find that in order to get meaningful structures, you also need to redefine the quantum deformation parameter kappa. Otherwise, your R matrix would diverge. However, if you do that, and then you take the 1/c going to 0 limit, you get a trivial result. So you need to do the contraction at the level of the co-commutators, and this is what you get. So this is the kappa de Sitter or kappa anti-de Sitter model, and this is what we get in the Galilean limit. In the flat, sorry, this is the kappa Poincaré. This is the flat case. In the flat case, this model was already found many years ago, and then we found it again when we did this. But then we were doing also the general curved case. So here, what we see is that we lose the feature of the Galilean relativity that there is an absolute time. So the main effect of the quantum deformation is that we do not have absolute time any longer. And this, in the end, can be traced back to the fact, I'm not going to show it here explicitly, but the non-commutative spacetime of kappa Galilei is the same as the non-commutative space of kappa Minkowski. So there is still a non-commutativity between time and space. And this is why you cannot have an absolute time in the end. And you see it here at the level of the algebra. When you do the Carroll contraction, it turns out that you can either do it at the level of the R matrix or at the level of the co-commutators. You get equivalent results. And this is what you get at the level of the algebra. So this is the contraction of kappa Poincaré. We see that here we still have absolute space. So in this case, the quantum deformation didn't do anything. Well, these are the other results. I'm not going to comment on them now. So what happens when, so this was in the flat case. When we also have curvature, so when we do the contraction of kappa de Sitter or kappa de Sitter, things become much more involved. So here, this is the Galilei contraction of kappa anti de Sitter. Let me just comment on a few features. We don't need to read everything. So we still have this deformed rotation sector. So we also have it in the Galilean limit. We still are missing the absolute time. But so this is the contribution from the quantum deformation, and then there is a contribution from both quantum deformation and curvature. And finally, what happens is that we have an effect that is due, again, to the fact that we have both quantum and curvature deformations, which is that the boosts are non-commuting. So this is a feature that would not be expected normally in a non-relativistic model, but here we have it because of the interplay between these two deformations. And yeah, of course, we still have that the translation generators do not commute because this is a curved model. And finally, the Carroll contraction looks much simpler. And in fact, this is an interesting observation that when you do the Carroll contraction, the effects of the quantum deformations become less visible somehow. I'm not sure why this comes out from the contraction, but it would be interesting to understand why this is happening. For example, we recover isotropy. We recover a standard algebra for rotation. Also, we recover the fact that boosts commute, even in the presence of curvature. And for the translation generators, we have that they do not commute because of curvature, but there is no additional deformation. I'm done. This is only one more slide. This is what we would have in the standard non-quantum case. So to conclude this concluding slide, it's a summary of all the features that we have when we look at all of these relativistic models. So here in the center is the kappa de Sitter model, where we have anisotropy, as I mentioned. We have, of course, non-commuting boosts with a nonlinear deformation due to interplay between lambda and kappa, and all the features that we have discussed. And then we see that Carroll contraction is restoring isotropy, but this is still there in the Galilean case. We have, again, so here you really see that in the Galilei case, the non-trivial features that we had in the full kappa de Sitter model are still there, while in the Carolian case, in some sense, is more standard, so to say. And I think we can conclude here. Thank you very much. I leave this on.
Questions?
I suppose your focus is on kappa Poincare, am I right?
Yes.
My question is, what is its causal structure, and can you construct a quantum field which is causal, given that the momenta don't commute? How does one
in the curved case?
In the curved, whatever. In the general case, can you construct what is the causal structure, and what is a quantum field? How do you construct?
Well,
how do I make calculations in quantum field?
But so you are unhappy with the non-commutativity of translations of the momenta, but this is what you have in the classical de Sitter model.
Classical de Sitter model, there are horizons. So that presents you with other, but the causal structure is understood there. So
yeah,
here one can construct a quantum field. For example, there is a recent paper by Witten, Longo, and Chandrasekharan, and they have a construction. Okay? Here, what do you do? What is the causal structure?
Well, I don't know yet. This is all recent work. So you saw the papers are from at most 3 years ago. So I think we're still far from there.
What is the dispersion relation for the photon?
Well, the dispersion relation, I can show you because I have it. It's what I wrote here. Sorry, it's a bit to go back. So this here is basically the dispersion relation for a photon, because it's the relation between energy, P0, and spatial momentum in 1+1 dimensions. In 3+1, we are not able to do it yet, but in 1+1, this is the dispersion relation. You see, this part here is the one you would have in de Sitter usually, so it's energy redshift. And then you have a correction term here that depends again on the momentum and on time, but I mean it's you can write it. This one you can write it, and of course this is encoding the fact that you will have an energy dependence of the velocity, as you have in the kappa deformed models when they are flat. So I mean there are issues with the causality there, because what does it mean to have a faster than light particle? But in the flat case, this is investigated. Here, not yet.
Okay. You also had a de Sitter momentum space in the table.
Yes.
What is this causal structure again? Is it in a horizon?
So the de Sitter momentum space is just a way to look at the kappa Poincare model.
Okay.
So it is that.
What is the phenomenological backing for all these models?
Sorry?
Why does one look at it? Where is the phenomenology? What experiment suggests these possibilities? Just like that.
Well, there are no experiments that suggest it. There are experiments trying to look for it. So there are experiments trying to see whether what I was discussing here, whether you might expect that particles with different energies travel at different speeds. So this would be a possibility, but I mean, nothing of this was seen. Otherwise, we would have Nobel Prizes, no, already awarded.
Any more questions?
You speak about the deformations, classical deformations and quantum deformations of Lie algebras, but I think if you don't take into consideration the coalgebra part, I mean the whole Hopf algebra, then you cannot distinguish them, because I think the difference comes from different way of dealing with coproducts. So if due to the deformation, you can keep primitive coproduct, it's a classical transformation.
Yes.
If there is no way of keeping primitive coproduct, even when you change the variables, I mean, then this is quantum.
Yeah, I agree perfectly. I mean, I didn't talk much about the coalgebra because I didn't need it to explain what I was doing. But here, for example, I mentioned that the main feature of a quantum deformation is exactly that you are deforming the coalgebra. Then I didn't show all the time of the coalgebra just because.
Yeah, it's just
but I completely agree that a classical deformation does not affect coalgebra. A quantum deformation does, and there is no way to make it.
It's just purely terminological.
Yes, yeah, I agree with you.
There is one, Fedele.
It's a curiosity stimulated by Jurek Kowalski, the question. You have chosen in this case a space-like vector. I suppose if you take a time-like, so you go from de Sitter to anti-de Sitter, what happens in any case if you choose a null vector?
Where? You mean in the R matrix?
At the beginning, when Jurek asked whether you had chosen a direction, you answered,
well, no,
yes, there is a direction there.
Well, there is so when you do the Kappa-Poincare model,
yes,
in principle, there you could do a more general Kappa deformation, yes, which is using a general, yes, a generic yes, 4 vector.
Yes.
Then the specific, and you get different kind of spacetime non-commutativity, yes, as well. I mean, this, yes, you know. When I'm not sure.
When you do the extension,
when I do the Kappa de Sitter or
Kappa de Sitter,
there is another.
You have another you choose another direction.
Yes, so I start from the Kappa-Poincare, yes, where I chose that vector.
That's right.
And
then you have a further choice.
Yes.
And you have chosen a space-like vector because you have chosen the z-axis.
The choice here is on a 3 vector, not on a 4 vector.
Well, why? Because you can put eta.
No, eta is just the curvature. Here, I only had to choose which spatial direction.
Can you put their product between two, in the R matrix, between two boosts, or a boost and
no,
and the rotation?
So
you cannot.
It needs to be 2 rotation generators.
Okay, otherwise the thing doesn't.
So in this sense, I was saying that this is unique.
Okay.
It's unique in the sense that.
Well, I think Jurek and Andrzej should know. Is there the only possible extension of Kappa-Poincare to SO3141?
5 vector, no, not 3 vector.
5 vector.
5 vector.
So we are speaking about de Sitter or anti-de Sitter.
No, but okay, fixing one of them, then it's a 3 vector.
So this is 5 vector.
If I fix the sign of lambda.
Okay, so we thank Giulia once again.
Thank you.
And we go to the final talk for today. And the talk is by Albert Much. Is it correct? Yes. Okay.
Yes.
And the talk is not here yet. Maybe while we are looking for the talk, I just remind you that tonight we have a welcome reception in the garden here, and it starts at 8 o'clock. So in the garden in front of the museum. Okay.
Okay, thanks for the organizers for this wonderful conference. Today I will talk about non-commutative quantum field theory in curved spacetimes, or quantum field theory in non-commutative curved spacetimes. So the motivating question for me to do this is the question, does non-commutative geometry award us with a theory of quantum gravity? And the approach I take is rather, I start with something that we sort of well know, which is quantum field theory in curved spacetimes. And I try to deform this in a mathematical consistent way that it sort of agrees with certain principles that we take for granted, like the equivalence principle. So if you consider quantum field theory in curved spacetimes as a zero-order approximation to quantum gravity, and you consider non-commutative geometry to give you some quantum gravity, then I mean, if we are optimistic, let's say, or pragmatistic, then what we want is that at least non-commutative geometry applied to this framework should give us a first order approximation of non-commutative geometry, of quantum gravity. So this is sort of the idea. And so I want to fuse non-commutative geometry with quantum field theory in curved spacetimes. I don't want to go to the trouble of, deforming or doing non-commutative gravity and then trying to apply it to quantum field theory. I go to the basis directly. So basically, we have a framework of non-commutative quantum field theory in Minkowski space. And what I want to do is I want to generalize this to curved spacetimes. And I want this theory to comply with the equivalence principle, because I mean, even a theory of quantum gravity should somehow, have this principle in mind. So, as I said, I mean, why I want to do this? Well, I want a theoretical proof, at least, that non-commutative geometry or quantum spacetime is really physical implementable. And in a sense, by doing that, I want to supply a proof that it has a connection to quantum gravity. Okay, so a short intro into quantum field theory in curved spacetimes. Quantum fields are rigorously constructed for, let's say, globally hyperbolic spacetimes. Okay, so that has advantages. There exists a direction of time. There's a well-posed Cauchy problem, so you can define your wave equations on it and so on. The disadvantage is that in general, there is no preferred state. So, yes? You have to quantize the? That's why I say it's a zero-order approximation. Quantum field theory in curved spacetimes is a zero-order approximation. Of course, you're right. There's also the back reaction, and there's a lot of, there's then semi-classical gravity. But let me first do the zero approximation and then think of how to proceed. So as I said, disadvantages, there's no preferred state. So in Minkowski, we have the vacuum. It's a translational invariant and Poincaré invariant state. But in general, you don't have these symmetries. And in order to avoid all these problems, you do the GNS construction. So for any given state, positive linear functional over some unital star algebra, this star algebra is basically generated by the Klein-Gordon field. And one obtains a quadruple, so a Hilbert space, a dense subspace in that Hilbert space, a representation of your star algebra elements, and a sort of vacuum state, if you will. Psi omega, it's a cyclic and separating. Then the fields are given by some densely defined symmetric operators on this. And then I don't know what happened here. The endpoint functions are given by products of these and taking the expectation value. Yeah, I don't know why this is a big, I think there was here, so this should be the same f. So you take phi of x, this is a operator value distribution, and you smear with a test function in order to make this in a sense consistent. Sorry, this f should be the same. So it's a c in 0 infinity. And we have preferred states in that context, which are Hadamard states. And the reason we take, there are many reasons, technical and physical and so on. But I would say the main reason is they resemble the singularity structure of Minkowski. So if you take the Minkowski 2-point function and you look at the singularity structure and you take these Hadamard states, the singularity structures agree. And this is what I would call, and I never heard that before, and it's probably not quite correct, the quantum field theoretical implementation of the equivalence principle. Because no matter how curved or weird your spacetime is, if the equivalence principle holds, that means that locally in small regions, you still should have this singularity structure. Okay, there's a certain definition for these Hadamard parameters, and I think a lot of you know this because, I mean, I first did my master's with Harold on matrix models, and we did the heat kernel expansion, and this is exactly basically what comes out. So the Hadamard parametrics is like these u and v are some c infinity functions, and this sigma is made out of the geodesic distance function, so the sinh function, and t is some local time coordinate increasing towards the future. But you see, there are two. So for x goes to y, there is a certain singularity here, and this is the singularity of the 2-point function. So these are your preferred states. You have your algebra that is given and governed by the Klein-Gordon fields in curved spacetime, and then you have a state. So you can do the GNS construction, and then you have Hilbert space, and you can start doing physics. So now, how do we generalize this to the non-commutative framework? That this is a question. So basically, I say we have to generalize the star product to curved spacetimes. Why? There is sort of a intuitive idea floating around. So basically, quantum field theory in Minkowski spacetime is given by a well-defined procedure and so on, done by DFR in 2000-2001, where you have this field operator, and it is somehow represented by this tensor product structure, where these x's are the x's that generate the Moyal-Weil spacetime. Now, this can be mapped by a unitary transformation to some fields that are a little bit neater. And if you take the vacuum expectation value of many of such fields, it turns out basically that this is equal to the star product between these fields. So somehow the deformation and this vanishes when you take the vacuum expectation value in Minkowski space. This is what you refer to in your papers as the dress transformation. This was done by Harald Grosse in 79 in another context, right? So in a sense, and in quantum field theory, this is what it's about, endpoint functions. In a sense, you can start defining your star algebra and so on, but when it really comes down to specifics, it's endpoint functions. And since here it's given by a star product, I want to generalize the star product to curved spacetimes. This is my approach. I have no idea if it will work or not. So there are many technical problems. So this is the star product, maybe written in a way that most of you are not very familiar with, but it's also called the refill product. It's a way to make these oscillatory integrals well defined. So if f and g are some functions of compact support, this is not, so C infinity compact support, this is not a problem. Otherwise, you need a cutoff. But okay, the technical problem, the real technical problem is there are no commuting translations that lead to an associative product in curved spacetimes. In general, you don't have translations. So that is something that is an advantage of Minkowski, unfortunately. or fortunately, I don't know. The idea so first, my colleague and I were looking at this in Rindler, and it didn't really work. So we tried to generalize it by doing some exponential maps. And then we tried the case of de Sitter because Marcus is an expert in de Sitter. And this also didn't work for a long time. And then so Marcus came up with the idea, how about we embed this space-time, the de Sitter space-time, in a higher dimensional Minkowski? Then you have translations, because in Minkowski you have translations. And then you sort of pull it back so that you can define a star product. And that worked out pretty fine. And then I generalized this idea to all globally hyperbolic spacetimes by this Trump-esque title. I published it, Make Deformation Quantization Physical Again. Yes? I'll come to that. I'll show you how. So I mean, you can take a sphere, embed it into a higher dimensional flat, right? And then you can invert the coordinates, and then you can sort of play around with this, but I'll show you in a second. So now, how do you embed a globally hyperbolic spacetime into a higher dimensional Minkowski space? There is a theorem, right, pretty recently done by Sanchez and Müller, which tells you let this manifold be a MG be a globally hyperbolic manifold. Then it admits an isometric embedding into a higher dimensional Minkowski space for some n that is larger than your dimension. Yeah, that works. This is basically like the Riemann embedding theorem, but for Lorentzian manifolds. Actually, they didn't only show it for a globally hyperbolic manifold, they showed it for stably causal spacetimes, but okay. So that means there exists, you know, this map F with local coordinates xa, which are made out of x mu, yes? What is R? L is the Minkowski, is a higher dimensional Minkowski space. Sometimes it called it M, but since I have M's here, so Ln is a flat Minkowski space. Sorry, of dimension n. Correct. Of dimension n. Of course, this dimension is usually greater than the dimension of your manifold. Basically, the proof works very similar to the Riemannian proof. It's a very beautiful result. This means that you have local coordinates x mu and xa. Then you have these couple differential equations. Then there exists, you know, solutions for these differential equations. You know that by the existence of this map. You have n-4 constraints on the coordinates, so you can express. So you have now, let's say you're in 4 dimensions. You embed in this higher dimensional space-time. You still have 4 free space, so variables that do not depend on anything, and the others have some constraint. It's like with the sphere, right? You have the sphere, you embed it into R3, and then you have the condition x1 squared plus x2 squared plus x3 squared is equal to R squared. So x3 can be expressed as functions of the other 2 x's. And due to the inverse function theorem, you can invert that map. Now, you can define an associative star product. Since you have these translations, this product makes sense. You take Z and then you do the translation. If you pull back to your original manifold or the coordinates in the original manifold, this behaves as if this theta depends on X. And in a sense, this makes sense because the star product of Minkowski space is given by a constant theta. If you go to a curved spacetime, theta tensor should also change with the coordinates. So here J represents the Jacobian. Rest assured, it can be done. This oscillatory integral can be well defined if you choose certain cutoffs, but these are mathematical details that I skip over. And now for a star algebra defined on a globally hyperbolic spacetime, MG generated by Klein-Gordon fields, we have the following deformed 2-point function, okay? Now I take my fields, put the star product and write this in this oscillatory integral form. For certain functions, this is a well-defined oscillatory integral. And yeah, this is how you obtain the deformed smeared 2-point function. Yes? Yes, a very good point. As is any quantum field theory in curved spacetime, right? Unless you're doing it very, very abstract. But in the end of the day, you choose a metric and so on. But that is a very fine point. I will come to that. Actually, I've thought a lot about this. Okay, now you have your 2-point function. Okay, mathematical details here and there. What does that tell us? Is that mathematically well defined, or is it that, I mean, mathematically it's well defined, but does that have any physical sense? And to do that, we need to look at this very important theorem that I struggled a lot with as a student. Basically, okay, you have a bundle of non-zero null covectors, and you say a state omega obeys the micro-local spectrum condition if the wavefront set of this 2-point function is a subset of this n plus times this n minus. You might ask yourself, what is the wavefront set? So wavefront sets basically tells us where the singularity of a distribution is. Okay, so if you have a function that is C naught infinity, so it's smooth and with compact support, that means it has, you know, derivatives and all that, and it's a Fourier transformation. There are no singularities, so the wavefront set of such a function is equal to 0. If not, this wavefront set will tell you exactly in which directions your 2-point function or whatever diverges. So this is a little bit a mathematically rigorous definition. And there are a few useful properties. As I said, for Z not infinity, it has an empty wavefront set. And this is very important for this wavefront set. It tells us that if P is any differential operator with smooth coefficients, then the wavefront set of this PU, so of this differential operator applied to U, is included in the wavefront set of U. Okay. So let me say, so for those of you who are familiar with Minkowski spacetime, the 2-point functions, the singularity in plus and minus basically means you have positive and negative frequencies. Okay, this is sort of the very mathematical way to write it. The reason for all this exclusive math, so to speak, is the theorem given by Radzikovsky in '96. It tells you that the micro-local spectrum condition, so if you have some state that fulfills this micro-local spectrum condition, this is equivalent to having a state that fulfills a Hadamard condition. Okay, so you don't need to check if this is Hadamard, because in many explicit cases, it's very hard to do. All you need to check is if the wavefront set of that function fulfills this micro-local spectrum condition. Now coming back to our case at hand, the state omega, so let the state omega obey the micro-local spectrum condition. Okay, we have a state omega obeys the micro-local condition. Now I deform the state by this deformation procedure I just described, so basically a star product. Then omega theta obeys the micro-local spectrum condition as well, and the proof is a one-liner. If you have a strict definition for this, basically you can rewrite this integral as the star product, right? Of which many of you are familiar with. And then you can write this as P omega 2 of x1 and x2. The smooth asymmetric embedding guarantees the existence of, guarantees the smoothness of these coefficients. So it's a differential operator with smooth functions, coefficients, which means wavefront set of the deformed 2-point function is equal to wavefront set of P times the undeformed 2-point function. This is a subset of the wavefront set of omega 2. Okay, since due to this property of the wavefront set. And this is again in n plus cross n minus, which means basically again, this will fulfill the micro-local spectrum condition. And as a corollary, this means the deformed 2-point function is Hadamard. What does that mean? That means all these deformations basically that you generate in this way are physically meaningful since they satisfy the quantum field theoretical implementation of the equivalence principle. In regards to your question, now let's take another embedding. Okay, so you take another embedding and you can again show that this Hadamard condition is fulfilled. And then there is a theorem as well by Radzikovsky, which tells you that if the difference of two states is C infinity, then they have the same wavefront set. So basically, the wavefront set doesn't see the modulo, or it doesn't see if the functions just differ by a C infinity. Okay, so and that's how much. I mean, it's a bit of a mathematical thing, but in the end of the day, it's very rewarding in a sense because it clears all these irregularities or correct. Absolutely correct. Absolutely correct. It fixes Hadamard plus some C infinity functions, but the waveform set tells you it doesn't matter. It's a C infinity plus minus, so to speak. Yes. So in a sense, I hope I could convince you that quantum field theory in non-commutative or quantized curved spacetimes agrees with the equivalence principle. This deformation can be extended to endpoint functions. This is a bit a tricky part, but it can be done. And now we have a rigorous framework, in a sense, as a first order approximation. I mean, it fulfills the equivalence principle. That is a check. There's a principle that we are fond of, we know very well. And now we can start generating or examining all the achievements of quantum field theory in curved spacetime, as the Hawking effect, quantum energy inequalities, entropies. So quantum energy inequalities I'm working on right now. The Hawking effect I'm also doing with Rainer Ferch by a similar deformation method. And entropies, you can calculate also relative entropies in that context. And semi-classical effects, this is something that is in the future. And this will hopefully give us the opportunity or the framework to predict testable quantum gravitational effects. Thank you very much. Yes?
Questions?
I think no one is online, so we can.
Sorry. Okay, I'll object with the microphone. So I have an objection when you say that Hadamard state is a reasonable condition. So I think at the classical level, you might justify that, but at the quantum level, you're basically violating unitary. That's a trans-Planckian censorship conjecture. So there's no reason why.
But this is you're arguing about something semi-classical, right?
Yes.
Yeah, but this is, I mean, this is in a sense zero. I mean, this is before you go to semi-classical.
No, but you just said that you want to apply your analysis to Hawking radiation and things like that. And
yes.
I think you simply cannot.
Oh, no, this can be done. I mean, this is done in rigorous works by Rainer Ferch, Pinamonti, and so on, where they calculate the Hawking effect, without doing anything semi-classical. So you can just do it by relative entropies.
Yes, but if you want to do something which has anything to do with quantum mechanics, and the Hawking effect is supposed to do that, generation of fluctuations in cosmology is supposed to have something to do with quantum mechanics, you simply are not allowed to do the Hadamard approximation. So now I know this is a controversial comment. There's a whole community that does that. And I admit that what you've done very nicely is you've generalized the Hadamard prescription from to this deformed state. So I enjoyed your talk.
Thank you very much.
Okay.
I have a question.
Yes.
So maybe I misunderstood the starting point. So you said you want a star product on a curved space.
Yes.
Prevents you from taking any Poisson symplectic using Fedosov-Kontsevich, and then you get star product. Because I mean,
it's not well defined. I mean, the point is with the approach algebraic quantum field theory in curved spacetimes, the whole advantage of this, it's a very rigorous, well-defined theory that has to be touched, with pure reason, so to speak. And then, and I need oscillatory integrals to really make use of all these techniques. Just taking a star product is a bit. It's also not clear to me which star product I should take. Well, this is a more canonical approach in a sense. But yeah, I thought of that question as well. Maybe one can do it rigorously, but I know of no framework. Yes.
Right. So thanks. Maybe in line with this. So Riefel obtained these C-star algebras, right? Deforming the C-star algebras, like in a strict way.
Yes.
Do you get that as well?
Yeah.
It's a strict deformation quantization.
It's a strict deformation quantization. There has been a connection made by Buchholz, Lechner, Summers in a paper in 2010, where they basically show, so what I sketched here, so if you have phi theta, I mean, you can take, so to speak, the bounded algebra that this is generating by. And then you take a theta, you multiply this with another operator. It's a bit more complicated. I'm going to leave some details out. But in the end of the day, what you get is so to speak, the Riefel product, and that whole thing deformed again. So in a sense, what we do in non-commutative quantum field theory in Minkowski space is we really deform the field operators. And this warped convolutions method applies to that. So basically what it is it's an isometric representation of the Riefel product, if you will.
All right.
Yes.
So maybe one more conceptual question
Yes.
maybe related to this is that so you're not really considering your field theory to be defined on this non-commutative space that you're just describing by the star products.
Yes, you do. Yes, you do.
But
And
why do you care so much then about equivalence principles that are defined, I think, on the classical space?
I think so. In a sense, I'm old school, if you want, and I like the equivalence principle. And I think, I mean, we should have some principles when we move on. And I think the equivalence principle has proven, in a sense, very useful. So that, in a sense, locally, you should always get Minkowski or non-commutative Minkowski, if you want, right? But in there, so yeah, this is, so to speak, my holding point.
Okay. Okay. Thanks.
Your construction, as I understand, is based on this embedding theorem that if you have a curved manifold, you can embed it in a multidimensional flat manifold.
Yes.
But this physically, I think it's not. I mean, you're speaking about kind of high mathematics, but I think in this point, the important point is to understand what does it mean physically, these extra dimensions.
Yeah.
Before you, I mean.
No, but I'm not using extra dimensions. I mean, I'm using them as an auxiliary object, right?
So just take a simple example of curved
we did.
part of the Einstein theory, I would say.
Yes.
Just try to show how to even without fields, just what does it mean, this higher dimensional manifold, which is the flat manifold? Because on one side you have a curved physical manifold, on the other side you have this mathematical multidimensional flat manifold.
Yes.
Yeah? So this multidimensional flat manifold, before you just start to operate with it, you should understand better. I don't know.
I agree with you, and I was hoping that this Hadamard condition, this microlocal spectrum condition, or the equivalence principle, will narrow it down, or so to speak.
No, I think this kind of.
But let me also say, I use them purely as an auxiliary object. It's
No,
like
but
it's like when you use. Just let me tell you another example from physics where you have fermions and you cannot construct coherent states with them, and you multiply them with Grassmann variables, and then they behave like bosons. Then you can construct coherent states with them. This is purely auxiliary, right? Auxiliary objects that at the end of the theory don't really appear anymore. This is basically in the same spirit. But I agree with you. I mean, there has to be a better understanding.
So I think going into high mathematics is a how one says, for example, in French, a pâté bourgeois, you know, you use the high mathematics.
No, I'm not bourgeois. I'm proletarian, please.
You use this high mathematics. One should really, I would say, see what does it mean, this embedding business.
Yes,
you know?
I agree.
I know that people were trying to use it, you know, but no physical, I would say, counterpart of this embedding exists.
Yes. Yeah. No, I agree 100% with you. Yes. Father Chandran had a question.
I mean, this is an issue of this Hadamard space. There are many of them. Okay? They are not at all unique normally.
Yes.
And the trouble is in picking the right one when you right. A related question is there is an attempt by Fredenhagen to apply Hadamard space to FLRW. For cosmology, for the Friedman limit of that metric.
Yes.
And he told me he did not pursue because he was not happy with what he had done. But maybe you have a method of applying it again to cosmology. Okay. I'm just asking. Then the question is, once you have the 2-point function, you can extend it to n-point function as a quasi-free state. right? You can just apply the quasi-free condition. You have all the endpoint functions.
Correct.
By Wick's theorem. Okay?
Yes.
So you have at least one way of quantizing this 2-point function already. From what you have written, I think you already have. But I don't know how you pick the Salaman state. There is also another condition, Distelmach-Hellman condition for the propagation of singularities.
Exactly. This is the wavefront set and so on. Yes.
That I think is automatically fulfilled in Hellman state. I'm not remembering.
Yes.
But that condition is very important for the propagation of singularities as time progresses.
Correct. Okay. I mean, this wavefront set turns a blind eye to any inequivalences in a sense, because all it cares about is what happens when the x goes to y. So where the singularities are. Everything else it doesn't see.
Yes.
And this is enough at least to say there is a Hadamard. Now how that looks and how that explicitly can be constructed.
We are picking one. Do you have a pick?
No, I don't pick one. I say there is a Hadamard state. There exists because on globally hyperbolic spacetimes there is.
I think it's a very nice idea that you have got.
Thank you very much. Yes.
So when you embed a curved space in a flat space, and then you want to take the product of two functions on the curved space, you need to extend a little bit to the flat space.
Yes.
And then take the star product on the flat space, and then restrict it to the curved space. So are you sure this procedure doesn't depend on the extension of functions and doesn't depend on how you embed the curved space into the flat space?
No, it depends on how you embed the flat space, the curved space into the flat space. But the end result, this wavefront set, doesn't care about how you embed. It just tells you basically you have the equivalence principle by having this Hadamard condition or this microlocal. It doesn't tell you exactly. So I was hoping this will pick out some states or some embeddings, but unfortunately it went completely through. Yes, but it depends. Yes. So I think we should have this discussion.
At 8 o'clock, as we know, we will have this reception, and we hear some music from Epirus, which is the land opposite of Corfu. It's the first possibility in the mainland. So usually we have Corfu tours, but tonight we will have something else. So the way to go is as you come up, you go straight towards the museum. You can make a cross cut, you can make a cut if you go through the garden, right? So slowly we can go there.
I don't understand on